It's great to be here. I'm very excited. Yavo, my student, PhD student, was here last year, and he was so excited that he said, Philip, you need to come here. And so thank you very much for the invitation. Yes, I'll talk about an approach that we are addressing that kind of brings together computer graphics, simulation, and AI. And that will be the core of my talk, but I'll talk quite a bit about rendering as well, and some of the technology we use to make that possible. So my name is Phillipp Slusallek. Originally was a physicist. I moved into computer graphics, and about 11 years ago, moved into AI as well. I'm currently at the German Research Center for Artificial Intelligence, and I'll quickly start by giving you a quick overview of what we're doing. So the DFKI, the German Research Center for Artificial Intelligence, we're trying to build computers with eyes, ears, and common sense, more and more common sense, hopefully. We're, as far as we know, still the largest AI research center worldwide, despite the big investments in the West and the East. We have 6 sites across Germany, almost 20 research groups, more than 1,000 people, many spin-offs that we're generating. So we're an applied research center. And we're actually a private research organization. Our shareholders, you see them here on the list, so Microsoft, Google, Intel, a lot of people from the car industry and many others. And as you see, we're distributed across all of Germany, essentially. I'm actually coming from the Saarland, so this is the part here in the lower left, right on the French border, near Luxembourg. And so on this campus, we have the university, we have 2 Max Planck Institutes in computer science, and then the DFK, and they are obviously on basic research, and DFKI is a very application-oriented institute on AI. And together we have a large cluster of excellence, which is a German excellence program in science, and there is a big new startup institute. It's more than 100 people now in the IT security area. So there's a lot of collaboration, a lot of great work right on the campus, probably one of the best places to study computer science, at least in Germany, maybe in Europe. And my group, called Agents in Simulated Reality, is at the university, where we do the basic research, and as the DFKI, and we're trying to bring together computer graphics and simulation, artificial intelligence, as well as high-performance computing. And I'll talk about different pieces of that in my talk today, and we'll collaborate a lot with the other players on campus. And we're very international. About 1/3 of our researchers is from worldwide. Over 60 countries are represented. And I should mention, we are hiring. So what are we doing? What have we been doing? So we have done a lot of the original real-time ray tracing work in the early 2000s was done in my lab, which essentially led to products like Embry optics. A large part of the Embry team actually is PhD students from my group. I myself, in my sabbatical, together with 2 other PhD students, we're part of when optics, what became optics later, was started at NVIDIA, and lots of other companies as well using this now. We did a lot of work on the lighting simulation side, actually with a lot of people from Bulgaria. Ilyan Georgiev is from here. He is behind VCM. We heard about VCM early today. But a lot of other stuff. Yavor, who was talking this morning, has been contributing that more on the GPU side, and many other stuff. And in 2005, we actually developed an FPGA for real-time ray tracing. And as you all know by now, it took just 13 years from that paper to be realized in now being available in all of the NVIDIA graphics card. Of course, that is probably a greatly enhanced version of what we had back then, but it's great to see this research going eventually into real hardware and into the hands of all of you. I will talk a little bit about, so we're not building hardware ourselves at the moment, but we're building a big compiler framework, and I'll talk a little bit more about that later. And we're working, and that leads over to the digital reality work we're doing. We're doing a lot of work on simulating humans, but in the factory we do that with Daimler, humans and robots working together. We do this with Volkswagen and Airbus. And we're doing a lot of work on autonomous driving. And I'll take this as an example. So what is this digital reality thing, and why do we need this to train and in particular validate AI systems? And what does computer graphics and rendering play in this context? So some of you might have seen this image. This is the image of the person that was crossing a 4-lane street when an Uber car was approaching. And even though the car was perceiving the person for more than 6 seconds, the AI in that car decided, oh, nothing to worry about, just go on driving. And it did nothing, right? That person, that woman with a bicycle, quite well visible. It's actually not that dark. That was taken at night, in the next night, with a apparently better camera. That person was hit and eventually died, right? So the worst thing is not so much that the AI failed. The worst thing is that the developer of the AI system didn't even know that their AI is so bad that it wouldn't deal with that situation adequately. Because we can't measure and we cannot validate the functionality of AI systems today. And so that's something we need to do something about, right? And here's the problem, right? The world out there is dramatically complex in terms of geometry, in terms of appearance, of motion, weather, all sorts of other things, right? Extremely complex. And still, we need to build AI systems that, under all circumstances, reliably makes the right decisions, right? I usually take the example of a kid running in front of a car, right? You really want to make sure that the AI system is capable of handling that situation appropriately and under all circumstances. And it's already very difficult to have enough training data for AI systems today. But for such critical situation, in particular, a kid running in front of a car, right? Luckily, that happens almost never, right? Which means you don't have data for that situation where you really want to make sure that the AI system does the right thing. So that doesn't add up, right? So, so what you need to do to really make this work is you have to synthetically generate the data that's necessary for learning. And essentially run virtual crash tests using virtual synthetic data. And if you think about it, this is exactly what the car industry is doing, right? They design a car almost completely on the computer. They do all the crash tests in the computer, and then they run a few cars against the walls and other things just to make sure that the computation was correct. So most of the crash test is virtual today. And also, like, if you look at the airplane industry, right? A pilot is not allowed to fly a car, well, a plane, obviously, unless he has in dozens, even hundreds of hours in a flight simulator proven that he or she can handle all of the emergency situations in a good way. Only then is he allowed to actually carry passengers in the airplane. And that's kind of what we need for AI systems, right? We need to be able to say, yes, this is fit for purpose and can go out there and we can use it for driving. And that technology doesn't exist today. So I want to talk a little bit about how we can build that technology for better training AI systems, but also in particular validating AI systems. And this is where computer graphics comes into the picture. So in theory, you could train and validate your car in reality, right? Just drive it around, and that's what they're doing, right? And there's a lot of discussion how many millions, hundreds of millions of miles you need to drive a car for it to be safe, right? That's the most stupid statement you could ever hear, right? Why? Well, that simply means, right, if you turn this around, it simply means you drive your cars as long as you've hit enough kids so that you have enough data to avoid this in the future. Right? That's essentially what all of this is about, right? That's obviously, if you formulate it this way, this is very obviously the wrong approach, okay? And so doing this in the real world just doesn't scale. It's way too difficult, too costly. Okay, so that doesn't work. So the next thing that the car industry has figured out is, well, we could do simulations, right? Why not do this in a digital reality? And they're doing this. At least they've started doing this. Now, what they're using for this is mostly computer games. Actually, the first paper published in this area was using GTA Grand Theft Auto. They patched the OpenGL driver, captured images, and used that for training an AI system, and actually improved the situation a little bit. And it looks great, the image, but if you compare that to the real world, right, there are differences, quite significant differences. Right, so the quick question is, where do these models actually come from? And do the pedestrians in these situations actually walk like real pedestrian walk? And the answer is pretty much no. Okay, so that doesn't really work either, because you would have to hire thousands, tens of thousands of artists that would really understand how people are walking and then create really realistic walking animations, for instance. So that doesn't really work either. It works to some degree, but it doesn't really scale. So here's where our idea comes in, and we're working on various pieces of this. So this is not a working system. This is what our research is all about, and we're building this piece by piece, and we're inviting lots of different people and other research labs and industry to work on this together with us. So the first part is, well, we take reality and we learn models about people, about how reality works. Right? This is actually similar to right, what a lot of computer graphics people are doing. Right? There's people who build models of materials by measuring that. And there's a lot of machine learning usually involved in this. And right, so build models about geometry, material, behavior, motion. So one of our work that we're doing is really building highly accurate models of how pedestrians are walking, how they're crossing the street, and lots of interesting pieces about that. So once you have all these partial models, because each model is only about one aspect or a couple of small aspects of the real world, so you need to bring them all together. And once you can do that, you can model critical scenarios, just like a kid running in front of a car, right? And it turns actually out that the car industry has large catalogs of critical situation, right? If we were just able to model those environments, animate them, render them realistically, we would be in great shape, because we would cover a lot of the parts that are right, that an AI system would have to handle robustly going forward. But it turns out being able to have such a single situation is not enough, right? And it probably still involves humans in this modeling these scenarios, at least to some degree. So we want to automate this. And in particular, we don't just need one kid in one specific situation to run across a car, in front of a car, but we need all sorts of variations, right? Kids coming from the left, from the right, small kids, large kids, at day, at night, fast and slow, and whatever. But that's nice, right? We have a model of the world, so we can just modify the model parameters, do some stochastic, for instance, Monte Carlo simulation, or some other, people have used genetic algorithms, and many other cases here. So once we have all of these large number of instances of these scenarios, right, we can go forward and simulate them. So this involves animating the kid running for the car, animating all the other cars. There's a lot of simulation tools already available for the car, for instance, simulating the dynamics of the car. That's all well solved already. But we also need to simulate the sensors in the car, so we can generate for one specific model of a car, right, exactly what the sensors of that car would see of this simulated environment. Now, sensors, of course, involves cameras, so this is what this conference is all about, right? At least to some degree. I'll come back to that a little bit later. Right, rendering images for the optical sensors. But of course, cars have lidar. Well, that's not too far away. It's just laser beam. So it's kind of optical, but has its own issues. But they have radar, right? And radar is all about right? There's polarization, there's diffraction, there's lots of other things that we usually in optics don't care about. The wavelength is much longer. I'll come back to this later. So we need to expand dramatically beyond what we're doing in computer graphics typically. And then once we have synthetically generated all the sensor data, right, we have lots and lots of synthetic data that we can then use to train AI systems as the input, as if we had gotten those scenes from reality. We can use it to benchmark AI system, right, by just presenting the AI system with the same input that we used last month. Did it get better? Did it fail? Right? It's the usual testing that we're software engineers, we've been doing all the time. And that's the most important part, we're now able to also validate AI systems, right? We're just doing a target test case generation, kind of trying to cover all of the possibilities. Yes, it's a huge space. So there are lots and lots of challenges about how to do that. But it can be done. There's lots of statistical measures you can do about how well you're covering that space, and so on. And then the final part is that you then validate your results against the real world again, because otherwise you might have gone off on a tangent. And that's really important because that also then allows you to identify the cases where your model about reality might not be as good as you thought, all right? And because the car might detect a scene, I'm always talking about, right? Maybe there's a kid doing somersaults, you haven't modeled that. So when you see this, the AI algorithm would not be certain about the results, so you could record this and improve your models. But you have to improve your models anyway, even if they were perfect, right? Because, of course, reality is not static, right? Reality changes over time, particularly if we introduce autonomous driving. And so we have to update our models anyway, and we have to identify where they don't fit anymore. Now, I've explained all this in the context of autonomous driving, but it actually turns out that all of this works for any AI system as long as you can model the environment that the AI system interacts with, right? Of course, autonomous driving is a big topic. There's a lot of money right now in this area, but we're actually having a couple of projects where we apply exactly this approach to model the cracks in the packaging of chips with one of the big, huge companies, world leaders in chip production, and we're applying this in a number of other areas as well. It's really interesting. It's really a fundamental part. So I mentioned radar, so let's get back a little bit to rendering, now that we've seen why we want to do this. So radar is really interesting, right? Obviously, the wavelength is much longer than optical light. So geometric optics, meaning rays, are not sufficient anymore. At least we have to do additional things. We have to do some sort of wave optics, but we don't really have to go back to the roots here. Turns out you can approximate a lot of the wave effects quite nicely. And it's very interesting, actually. If you look at rendering, we mostly care about the diffuse aspects of objects, the diffuse appearance of objects, right? Highlights are important, but they're kind of icing on the cake. We really care about the diffuse aspects mostly. Now, radar is exactly the opposite because there is so huge amounts of noise, right? The only thing that the radar actually detects is the peaks in the signal. Now, diffuse reflection means the incoming energy gets spread over all directions essentially equally, which means you're distributing energy in all directions, so it won't give you a strong signal in any one of those directions. Where you have the highest peaks is when you have reflection, right? Where you have specular transport, caustic path, and actually multiple reflections from one car to the other and maybe then back. So radar works very, very differently, and we care about completely different aspects of that, of what we're doing. We need to expand ray tracing to do other things. It actually turns out, and I'll come back to this a little bit later, is that there is a lot of work of trying to identify exactly those caustic paths. We heard about that V-Ray has better caustic rendering here. So there's a lot of things that we can do here. And we actually started bringing together the radar people with the rendering, with the graphics rendering people to get the best of both worlds. And that's really interesting. There's another aspect that I want to throw out here. We've been thinking a lot about this. And this is the question, right? Is there actually a new market here, right? So there's the gaming market, we all know that. There's the film, the high quality rendering, video, whatever market, marketing, and many other things. But if you look at this, both of those markets are essentially interested in nice images that humans will look at, okay? And they actually do all sorts of optimizations and shortcuts and improvements and workarounds and whatever to keep image nice, even though we're not really doing, maybe rendering the images exactly as they should be. And a lot of the compression and other things take advantage of the human visual system not to have to render everything. Right? But for all of these applications, not in all cases, but in many cases, we have a strong need for correct images, right? It's not enough that a human looking at them, like in GTA, yes, you can be fascinating about the quality, visual quality and complexity and everything, but it's not a correct, even closely to reality, right? So essentially what I think we need at some point is essentially being able to put an error bar on every pixel, right? Saying this pixel is correct within 10%, right? With ray tracing, Monte Carlo sampling, we probably can't get much better than a probabilistic error bar, but that's probably fine. And so we really need something like predictive rendering. Actually, with Jaroslav and others, we just handed in a European project proposal where we want to drive things further in this direction. And that needs a specialized rendering engine that has a lot of the features that we're doing for optics, but still needs to be different. And it still needs to be optimized. And if you think about all of the optimization efforts that we're putting into optical rendering, and you have to do the same thing now for radar and many other things, that's probably not going to work because it's probably not a very big market. Well, at least we don't know. So the question is really, how can we specialize these algorithms to like lighting simulation and rendering in general to achieve high throughput, right? And there's a couple of things. The one is we need to automate, right? Get away from all of these manual dials that people have to adjust. So make things much more automatic. That was a topic this morning as well. But it's even more important in this context because there might not even be a human looking at those images and correcting bugs and whatever, adjusting knobs is just not an option. Things need to work out of the box without question. So I fully agree with Jaroslav. Said this is good here, but it's really a requirement for this kind of thing I'm talking about here. And the other, I think we need compiler technologies to really be able to take advantage of all the different hardware architectures out there. And I'll talk about these different things at least briefly. Good, so let's start with these adaptive algorithms. And one of the things we've been working on is making caustics better, right? So there are shots where, right, there's essentially caustics everywhere, and you really care about the caustics, and they're the most visual part. But again, this is not really what we're dealing with, right? We might have a scene where caustic is only relevant in small pieces of the sensor input, right? And then there's really complex scenes here, which mostly diffuse anyway, and enabling caustics for a scene like that doesn't make any sense. You would spend a lot of time doing generating photons for photon mapping or whatever. It doesn't make any sense. So this is where the human comes in and say, oh, for this shot I don't need it, switch it off, whatever. So last year, we did this work here, and it was motivated by this photograph out of a hotel room where you see all the buildings, right? And then there is a few places over here. If you carefully look, I hope the projectors, yes. You can see there's some reflections from the windows of the opposite windows of the house on the opposite side that generate reflections here. There's actually also light falling through the windows here, creating a shadow, which essentially is acoustics as well. And so, right, manually, so you have to go in and say, oh, I want to really see the caustic here, because you don't want to generate caustic data everything everywhere else. And so what Pascal, my PhD student, did, was also a paper together with the Prague guys, is essentially come up with an approach where we can determine the usefulness of a photon at a certain location in space here. So it's a very simple approach. You have all of the data anyway. It's just a little bit of extra computation to figure out how useful the photon is. And so you only ever generate the photons in these areas where they matter. So that was a publication last year at the rendering symposium. And so just by that algorithm, right, you don't need to adjust things anymore. It essentially happens automatically, where we generate caustics, where we don't. And that's exactly what we need. And as I mentioned before, caustics are really, really exactly what we need for radar rendering. So this is also a good match, will help dramatically, we believe, for radar rendering. Another example, and this is something, it's a collaboration with the Prague guys as well, is one of the key elements in rendering is multiple importance sampling. So at every point in time, you have to decide when you trace rays through the environment, do I need to sample towards the camera? Do I need to sample towards the light source? Do I sample between different objects in the environment in certain directions? And you have all sorts of techniques that you could use. And some of the techniques, in some situations, some of the techniques are better, and in some other situation, another technique is better. Right? And now you could actually evaluate all of them, and that's what is being done today with multiple importance sampling. You evaluate essentially all of them, and then the result, you weight the results, right? And if you figure out that this is a bad technique, you just weight this with 0 or close to 0. And if this is appears to be a really good technique for that, you're assigning a high weight. And these weights actually turn out to be between 0 and 1. So this is this paper. It will be at SIGGRAPH this year. Yes, in the past, these weights were between 0 and 1, which makes perfect sense, right? If it's a really good technique, you want to give it 1. I mean, the weights have to add to 1. You really want to be, right, this is exactly what I need. And if it's a bad technique, you don't want to use it at all. Okay? So, and if Vichu was kind of the first guy looking at this, there's a mathematical proof that the balance heuristic kind of is optimal from a theoretical point of view. And it turns out many people are using the balance heuristic, but they actually, in most cases, use the power heuristic where, right, you square the results, really. So it actually turns out to be better. And that's kind of funny, right? Because the theory says the one should really be used, and most people are using something else, but even that fails in certain situations. And so based on really some basic work by Jaroslav, we figured out together that actually it is advantageous that we can also allow negative weights, which intuitively doesn't make any sense, right? But it essentially gives you more freedom to optimize. And just by, that was work we did for SIGGRAPH again, jointly, while 2 of Jaroslav's PhD students were in Saarbrücken, working with Pascal, one my PhD student, and we figured out a theoretical way how we can compute the optimal weights, and they can be negative. Actually, in many cases, they have to be negative. And the result is really amazing. But there's a caveat. I'll come to this in a second. So in certain situations, we can actually, per sample, get a 10-time reduction in the variance. So in the mean squared error here, right? This is, oops, sorry, that was too far. Dramatic improvements per sample count. So that's an amazing result, a great theoretical result. We even figured a way how do it reasonably efficiently, but this is not the most efficient algorithm at the time. But this is a completely new way of approaching multiple importance sampling from a fundamental new way of looking at things, and I'm sure there will be more efficient ways of computing this in the future. It opens up an entire new space that we haven't looked at in detail. And the paper is actually online, preprints are actually online. If you just search for publication for my name, and you find it there. It's the second paper on that page. So this is really working on fundamentally new algorithms in the rendering context, improving things. Actually, Pascal has a number of other ideas, just preparing a new paper in this area. So we'll keep working on a lot of those aspects. Now there's a completely different thing that we're doing, and that is dealing with the fact that we need lots of different renderers, right? For optical, for lidar, for radar, and maybe something completely different. And right, it's probably not an option to use V-Ray and tweaking it enough that it does radar. That might not be the best technique. And so we're really fundamentally starting to look at how can we do software development that is much more efficient than how we have been doing this in the past. Actually, when we did our original real-time ray tracing work, almost 20 years ago, for in a better half of a decade, we've been essentially programming an assembly level. Right? And if you look at Embry, that's essentially what is in Intel. There's a lot of highly optimized assembly level code, intrinsic code, that allows them to achieve the performance. And Karsten, who's been doing a lot of this work, again, a PhD student from my lab, he is really great at tweaking things to the last bit of performance. But that doesn't really scale. And so we've been spending, together with the compiler department, the compiler lab at Saarbrücken, we've been looking at this problem. So, and the state of the art really is, right, there's optics on the GPU side, right? And then there's Embry on the CPU side, and either doesn't work on the other side. They're completely different code bases, and even the API is not compatible. So highly specialized, completely independent implementations, very complex code, very low-level code, lots of optimization being baked into the code that you really don't see the algorithm itself anymore, or at least it's hard. And the bad part of the story is the compiler doesn't do a lot of the work. It's really the human who has to do a lot of this. It's a little bit better on the GPU side than the CPU side, but still it's a pain. So is there a fundamentally different way of how we can approach this? And yes, there is, otherwise I wouldn't give this talk here. And that technique that we came up with is called NEDSL. It's a completely new compiler, very different than anything. Well, we're using a lot of techniques that have been around, but they have never been combined in the way that we're doing this. So essentially, we have a single language called Impala that's based on a unified representation. Again, a lot of novel stuff in this. It's very flexible. There's a new compiler framework that works at a much higher level than LLVM or GCC or any of the other compilers. And eventually, for code generation, we actually rely on LLVM. Now, and on top of that, you can implement your own abstractions, right? You don't have a DSL, domain-specific language. There are lots of domain-specific languages for image processing, but you have to develop your own compiler and your own language for that. And there's domain-specific languages for all sorts of other domains, right? But they each have their own compiler. Now, we don't need this. We, on top of this one language, Impala, we're building abstraction, but they're just libraries, essentially. And that means we can combine computer vision and physics and ray tracing and maybe all sorts of other things in a single platform, and they can interoperate very easily. Now, the really interesting part comes at the back end. We actually have support for CPUs and GPUs. I'll talk about this in a second. We have a prototype for an FPGA backend that was only tried for computer vision image processing application, but it got us great results there, and we're targeting accelerators as well, others than GPUs. So this is a lot where the interesting stuff is happening. So again, there's a SIGGRAPH paper coming up this year by Arsène, who will actually give a talk tomorrow. on exactly that work and how that works. And the idea of NEDSL, or rodent as the paper, the system of Pazen is called, is that with NEDSL we can write all of the ray tracing algorithms in a single time, once, in high-level code that really looks like textbook code of how to do intersection, how to traverse a KD tree or BVH, and all sorts of other things. It's very nice abstraction of the rendering. It really looks like textbook code, right? Nothing where anyone would expect that to ever run efficiently, right? It uses abstractions, which is just functional interfaces between that high-level code, and then we put this together to a full Monte Carlo path tracing architecture, but it's actually, right now it does path tracing, but it's actually not a big deal to extend this to bidirectional path tracing and VCM, and we have some activities doing this in the future. Then on the lower end of that, right, we have to add specific, hardware-specific code that implements some of the abstractions about how to traverse a number of rays, how to schedule the intersection computation, how to schedule the shading, and a lot of other things. And there's different code for CPUs, and there's different hardware-specific code for different versions of GPUs. I'll come back to this in a second. And that's the key part of NEDSL. There is the compiler contains a partial evaluator, which essentially symbolically executes pieces of code. There's some annotations in there. Arsène will go into a lot more detail tomorrow and explain how this works. That eliminates a lot of the overhead from these abstractions, and it optimizes the code wherever possible. Essentially what a very, very good, perfect optimizing programmer, developer would do. It's essentially done by the compiler here. And the result of that is a highly optimized renderer. And actually the exercise that we did in the SIGGRAPH paper is that we take a scene description, the parser actually generates a program in Impala, which gets compiled by our compiler, and the result is a renderer exactly for that scene, and it's optimized to exactly that one scene. Now, of course, you can go back to that and say, I only optimize for a certain class of images, for scenes, right? Where maybe I know that there's only triangles, no other primitive. I know there's only this set of shaders, and I can optimize for that, or anything. Or I'm doing radar rendering, and maybe you do your renderer looks very, very different. But of course, the ray casting code is probably the same. So we can optimize a lot of things with this, and that's a very, very nice piece of work. Now, what are the results of that? And that's where it becomes really interesting. On the CPU, we're actually beating Embry by 23%, right? And Embry is highly, highly optimized. Optics, because we actually, instead of an Uber kernel, a mega kernel approach, we're actually using a wavefront approach, and that gives us a lot of performance, and so we're actually up to 42%. So these are the best case numbers. And we're using CUDA or PTX to interface with the GPU. And just as the final version of the paper got out, we've also been able to make the whole thing run on AMD GPUs using the HSA interface, which is kind of the CUDA equivalent there. Slightly different, of course. So again, and the really interesting thing that I just want to point at is there is collaboration. Since Arsène was here last year, with Martin, there's a great collaboration. And Martin has done a lot of work to try this out and experiment on this data. This looks very promising. There will be a little bit more information tomorrow. And yes, we get very nice numbers for that. And again, the pointer to the talk tomorrow at 12:30 in this room here by Arsène, where he will talk about this compiler and his work that he did, which will be great. Now, having a compiler that does nice work for us is great, and we're getting great performance, but another measure is maybe even more important, and that is productivity of the developer, right? Now, it's very hard to measure that. Probably the best accepted measure for that is the Halstead measure, which kind of looks at the code with various abstractions. It's not perfect, but it's what is accepted in the software engineering environment. And so here you see the Halstead numbers for Embry, which is really high. Actually, on the GPU with CUDA, the abstractions are better. So the effort to build the same piece of code, we actually built the same renders on all of these frameworks and compared them. It's somewhat better here, but it turns out that using NEDSL, right, the common code is actually, the effort for writing the common code, the high-level algorithm is really, really small. And then writing the specialization for the GPU or the CPU is actually equivalently complex and much, much less complex than either of the others. So even writing all of these versions, all of these two, and now with AMD GPU, also that version, so there is a little bit, it's very close to the CUDA or the NVIDIA version, so their complexity is probably not much more. So essentially we can write all of those versions in the time it takes to write the cheapest version of just one for one hardware architectures. Okay, this is what I just said. Okay, so with this I'm essentially done. I want to leave some time for questions, so start thinking about them. So what I want to do as a takeaway, right, this idea that computer graphics and rendering is not just about generating nice images. Yes, of course, it's really important. That's why we're here, right? But there's lots and lots of applications of all of the technologies in other areas, and AI is really a hot topic right now. And all of what the stuff we're doing is directly applicable in this area, and there's a large research effort in this area which we're leading and pushing forward. And so this digital reality will be, I'm absolutely convinced, will be a key element of future AI systems, in particular to validate AI systems going forward. And with the ability to validate AI systems, we have built we are building the fundamental technology for coming up with trustworthy human-centric AI. AI where we know how good it is, we know what it can and cannot do, and where we can, in advance, avoid possible problems going forward. And that's one of the key topics of European AI. I'm one of the initiators of the CLAIR initiative, where we're trying to push this, bring the AI community together, and I'm very much advocating to the AI community that they need to look at graphics, rendering, simulation, all of this environment. And it would be great to get more people from our field here active in this area. But again, this is not a finished product, far from that. There's a lot of big challenges, unsolved problems. A lot of these things, as we can see, the compiler now being evaluated here by Chaos Group with very great results. There's a lot of very, very good intermediate results already. But the big vision certainly takes a while more, and there's lots of problems still along the way. And yeah, I'm pointing to this CLAIR initiative here, so if you want to know more, clair-ai.org, you can look this up. And so really my key takeaway message from today is don't just look at nice images, think about how graphics, rendering, simulation, and AI can work together. I think that's the real winning team going forward. Thank you very much, and I'm happy to take questions. Thanks.